You have learned that air pressure decreases with altitude. However, the vertical decrease of air pressure with altitude is not equal at all locations. It is determined by the temperature of the air column above the location. Heating causes a density decrease in a column of air. Air pressure over a warm air column is higher than over a cold air column at the same altitude. The altitude of a constant pressure level, for example 500 millibar, increases with the temperature of the air column beneath it. The columns below the 500 millibar level contain the same amount of air. The warm column has lower density to compensate for its greater height. Differences in air pressure in the upper atmosphere are best determined through the heights of constant pressure. The height contours indicate the pressure gradient. High heights indicate high pressure, low heights indicate low pressure. Twice daily, heights are drawn at 60-meter intervals for various pressure levels. Typical pressure levels are 850, 700, 500 or 300 millibar levels. For example, the 500 millibar level is approximately at 5,600 meters altitude and the 300 millibar level is approximately at 9,100 meters altitude. The lack of friction at higher altitudes leads to a balance of pressure gradient and Coriolis forces. Consequently, winds blow parallel to the isobars and are called geostrophic winds. Following what you have learned about warm and cold air, air pressure at the same altitude over the tropics is higher than over the poles. Consequently, air flows from the tropics to the poles in the upper atmosphere, and Coriolis deflection to the right, over the northern hemisphere, leads to a mainly westerly flow in the mid-latitudes. The jet stream is the most prominent feature in the upper air westerlies. It's a narrow band of high wind velocity in the upper troposphere. The polar jet stream is located above the polar front. The polar front is the region where warm air masses from the lower latitudes collide with cold Arctic air masses. The subtropical jet stream is located above the Hadley cell in the subtropical region. Winds in the jet stream are about twice as strong in winter as in summer. Average characteristics of the jet streams are a width of 100 to 300 miles, a depth of 3,000 to 5,000 feet, an altitude of 24,000 to 35,000 feet, and wind speeds of 190 miles per hour. Jet streaks are defined as localized wind speed maxima along the jet stream. The upper air westerlies are not strictly zonal winds. Starting from slight undulations, they develop a wavy pattern called the Rossby waves. Rossby waves cause meridional flow of warm air from the south to the north and cold air from the north to the south. They are a primary mechanism for poleward heat transfer. They bring tongues of cold air to the south and warmer tropical air northward. Low pressure systems can be pinched off at the troughs and form mid-latitude cyclones. The wavelengths of Rossby waves are about 4,000 to 6,000 kilometers. There are 3 to 6 waves around the globe. Elongated zones of high pressure are called ridges. Elongated zones of low pressure are called troughs. To understand what this means for our weather, we need to understand the concept of vorticity. Vorticity refers to the spin of the atmosphere. There are 3 different vorticities. Relative vorticity is the vorticity of rotating air relative to the Earth's surface. Earth's vorticity refers to the counterclockwise rotation of the Earth. It is a function of the latitude. And absolute vorticity is the sum of relative and Earth's vorticity. We define positive vorticity as cyclonic counterclockwise spin in the northern hemisphere and negative vorticity as anticyclonic clockwise spin. An air parcel traveling around a trough must turn counterclockwise, thus increasing vorticity. Simply because the counterclockwise spin of the air parcel complements the counterclockwise rotation of the Earth. So absolute vorticity increases. An air parcel traveling around a ridge must turn clockwise, thus decreasing vorticity because the clockwise spin runs against the counterclockwise spin of the Earth. Once more, we see positive relative vorticity in the region of the trough and negative relative vorticity in the region of the ridge. Again, traveling through the trough, the air increases its vorticity. Traveling through the ridge, the air decreases its vorticity. Here is again an illustration that shows what happens as the air moves through a trough. The air parcels at the positions 1 to 3 experience little change in direction and therefore no relative vorticity. The air parcels at the positions 4 to 6 experience counterclockwise spin and therefore positive relative vorticity. The air parcels at the positions 7 to 9 experience little change in direction and therefore no relative vorticity. The change of vorticity occurs in the transition zones A and B. At transition zone A, the air parcel experiences an increase of vorticity. At transition zone B, the air parcel experiences a decrease of vorticity. The physical law of the conservation of angular momentum states for a radial movement that the mass times the velocity times the radius of the curvature is constant. Our conclusion is, when the velocity of the movement increases, then the radius of the rotation must decrease if the mass remains constant. The picture of the ice skater illustrates this law beautifully. An increase in velocity is associated with a decrease in radius. A decrease of the radius of the rotation is nothing else but convergence. So at this transition zone A, we experience increasing counterclockwise rotation or increasing absolute vorticity and consequently upper air convergence. At transition zone B, we experience decreasing counterclockwise rotation or decreasing absolute vorticity and consequently upper air divergence. Upper air vorticity changes lead to surface pressure changes. Decreasing vorticity in the zone between the trough and the ridge leads to upper air divergence and rising motion throughout the atmosphere, which supports surface low pressure areas. Increasing vorticity in the zone between the ridge and the trough leads to upper air convergence and sinking motions throughout the atmosphere, which support surface high pressure areas. Here again, upper air convergence means a surface high pressure system, upper air divergence means a surface low pressure system.